All right, hello everybody, and welcome to the Steam Power Podcast for Saturday, February 22nd, 2014. We've got obviously a new set today. We are trying out the green screen technology, so bear with me. I have no idea what I'm doing, but I can see on my screen I got a little bit of like green right here on the edges around me. Oh well, we'll figure it out. Anyway, let's see here. A couple of stories this week, and got a question about what is systems engineering and what is it? How is it different from other engineering disciplines? So we'll do that. A couple questions. Um, I guess obviously the new product for the week is green screen, though you can't see green screen, um, except if I do like, oh, look at that. And I apologize if you're listening to this. You can't see it obviously, but anyway, so that's the new tool. This was on Amazon. It's a set of 3 lights and the green screen, muslins, the green and a black and a white. So I'll put a link up to that if you're interested, and the workflow that I'm using. Using 2 tools to do the camera. So there's let's see here. Well, there's a OS 10 app called Webcam Settings to help clean up the camera output, and then Cam Twist to actually do the layering of the webcam and then the background image. So with that, let's go ahead and get into. Actually, before we do the stories, let's go ahead and thank our sponsor for the week. Let's see if I can figure this out. No, I guess I'm just not smart enough to figure it out. No, here we go. Okay, so we go. Darn. So we'd like to thank Audible.com. They're the sponsor for today's podcast. You can get a free audiobook and 30-day free trial by visiting audibletrial.com/SteamPowerPodcast. Obviously, that helps us out a little bit too. And from there, you can find over 150,000 audio titles to choose from, all available for the iPhone, Android, Kindle, or your MP3 player of choice if you're still using anything else but iPhone or Android or the Kindle. So thank you to Audible.com for sponsoring Steam Power Podcast. All right, so let's go ahead and get straight into the stories, shall we? All right, so this week Google announced a new project called Project Tango, and from what I've been able to research and what I've been talking to other folks about is basically you take a Android phone, gut out the mobile phone part of it, and put in a lot of whiz-bang sensors and technology that allow you to map and interact with the 3D world, the real world around us. So, they've done a great job with Google Maps and Google Earth and mapping the outside world using satellites. So the next step, logically, is things like what happens when you're in the shopping mall, or if you're like me and your wife always sends you to a grocery store and she swears that, the baby formula is in aisle 5 and it's halfway down and it's right there on the middle shelf. And lo and behold, I always go in and I can never find what I'm supposed to find in the grocery store. Well, Project Tango is going to help that. And they've been working it, obviously, internal for quite a while, it seems. And I think now they're to the point where, kind of like Google Glass, it's like we've got it into this prototype stage, and now we want to go ahead and take it to the next level. And that really requires people to actually kind of jumping in and beta testing it as well as developing applications. Because, frankly, your imagination is only so once you on a team, eventually everyone starts to suffer from groupthink. So getting it out to independent developers um, helps the development process and take it another step forward. So, um, they talk about what you can do with it. They also talk about, just like their self-driving car, helping visually impaired or other disabled individuals, basically live a more full and rich life akin to someone who does not have any disability, kind of equalizing that world, which is, I think, very smart on their behalf or on their part. Um, I think there's a lot of resistance to the idea of self-driving car, but when you fire back, okay, but what happened? What about if it's for a person that's visually impaired and has spent their entire life dependent on other people, giving them that freedom that is a self-driving car to live their own life? Well, it's kind of hard to argue against that. Um, so I think this is same thing. Is so there's gonna be privacy concerns, but you fire back that like any technology, literally any technology, there is technology we can use for good or bad. Um, and I personally can't can't wait to see it actually. Again, they've got about 200 prototype units. um, and if you go online, you can fill out a form and tell them how you would develop it and what you would develop, and they'll based on those they'll make a decision on who to send the prototypes to. Now, there is a video. I'm gonna see if I can launch it. Oh, and the team is led by Johnny Lee, who, if if you've watched YouTube in the past few years, he was the guy that did a lot of research into basically hacking when the Nintendo Wii was pretty new, the original Wii, and the the Wii remote, the Wiimote. He did a lot of cool projects of doing like DIY virtual um, whiteboards and some other cool tracking by looking at the hardware. So I knew he had gotten involved with Google, and this looks like what he's been working on. So it's pretty cool. And if I can, I'm going to go ahead and fire up the movie here. See if I can do it through the tool real quick. Bear with me. All right. Add videos to the playlists. Search. Okay, so let me go ahead and exit the screen chat. So that's Project Tango in a nutshell. I think it's pretty awesome. Um, uh, if nothing else, um, like I said, I really believe in the idea of enabling the visually impaired and other disabled to um, live a more quote unquote normal life um, is extremely powerful, and wish them the best of luck. So, with that, let's go on to our next story for the week. We don't have too many this week. So, here we go. Um, this comes to us from Wired.com, and it's a story about a group of researchers, I believe it was at Harvard, who are using a principle called stigmergy, which basically is a minimalist strategy um, that assumes that animals or insects like termites, in this case termites, you know, the way they work together to accomplish things like um, developing these huge, massive termite mounds is not a very complex process because they don't have big brains. They're not very. They're the intelligence, quote unquote, is not that advanced. So what do they do to compensate? And then how can we mimic that in robotics and electronics? So the story it's a really it's a good read. It's a simple read. It talks about how when uh, termites, when they're building their mounds, they're not following to some master blueprint that was preconceived. It's all an innate, uh, um, you know, it's kind of imprinted. So what they do is, termites they go in, they scoop up mud balls, they move them around, and then as they go, they leave a chemical cue for the next termite that follows behind them. So, um, and then all this adds together, and you eventually get pretty amazing structures. Not only that, are they impressive of themselves, but apparently they're also aligned to like the Earth's magnetic field. Um, so there's a lot of sensing going on, whether or not the termites realize it or are thinking it. They are reacting to inputs and stimulus. So the Harvard robots have kind of they're mimicking that strategy, and so they're programming very basic functionality. Move forward, move backward, turn, and then picking up and setting down the bricks. And then they talk about, and I'm assuming there is some equivalent to a chemical cue that they leave behind, which they unfortunately didn't talk about. The article was a little light on the details, but obviously there's something that's being coordinated. I don't know if it's a mesh network or some other sort of mechanism that communicates to the other robots, hey, I've placed something here, um, and then they can, the other or the other virtual or robotic termite knows how to react to that. So pretty cool. Um, I think I always like stories that question, really what is intelligence, and I think sometimes we make it more complicated than what it really is. Inputs, process, outputs, and simple algorithms that just the way they work together and how fast they work is really the intelligence. But anyway, pretty cool. Okay, next story. A group of engineers between um, NASA and MIT um, have built a system for laser communication that has produced data transfer speeds of up to 622 megabits per second. And not only that, but that's based on traveling um, from a spacecraft orbiting the moon to Earth. So I apologize for the fact that I'm sitting down here in beautiful Southern Maryland with my uh, lovely internet service provider, and I'm barely tweaking out 15 megabits per second. And here we now have um, laser communication from the Earth to the Moon at 622 megabits per second. Um, Interesting, huh? So anyway, it's a good article. It talks about the project is called the Lunar Laser Communication Demonstration, and goes on to talk about why this kind of data link is speedy. Today with satellite space probes that use radio frequency communication, it's slow. It takes a while. Um, the data rates aren't very fast, and they think somewhere in the article they talk about the fact that it would take decades to do the equivalent of Google Earth for Mars and transmitting that back to Earth as a satellite um, goes around Mars. With this system, they can do it in about a year. Enough they could get enough data, the equivalent of the data that we have for Google Earth for Mars, and transmit that back to Earth in about a year. So it's pretty cool. They also talk about the test was basically which is very rare in the engineering world. They said it was kind of a letdown because it just worked. Everything, even cloud coverage, atmospheric anomalies, you know, knocked it, a little bit, and when the moon was kind of close to where the sun was in the sky, it dropped down to a measly 322 megabits per second with about a 7-second lag. So I would take those. I would take those kind of speeds with my ISP um, if I had the opportunity. But anyway, um, and then they're going to follow up with what's called a laser communication relay demonstration, which is scheduled to launch in 2017, and provide gigabit Ethernet or gigabit, excuse me, internet, connectivity between Earth and a geosync satellite. So kudos to the folks involved. I think Vint Cerf is in. I would imagine he's would be looking at this kind of stuff too, and reimagining a what does the internet look like in the interplanetary sense. Once we become a truly multi-planet species, we're probably still going to want to have things like YouTube and Facebook and Twitter or the equivalents at the time. And then long term, and then at least initially, we're going to have to do communications, just for health and safety reasons. So, but how do we do that, and how do we move past simple radio frequency? So, it's cool. Like I said, I would take those internet speeds in a heartbeat. All right, and our last story for the week, we are apparently one step closer to nuclear fusion. So I'll try to do my best to explain what I understand. So for the first time, more energy that reached the fuel, which in this case is I think they're hydrogen isotopes, deuterium, and yeah, hydrogen isotopes. So you take a little pellet, coat it with gold, fill it with a little bit of hydrogen isotopes, and bombard it with lasers. In this energy, in this case, they use lasers. The gold emits X-rays. X-rays then heat up the fuel. The fuel begins to react, and you start getting energy out. Well, for the first time ever, from what I understand, the amount of energy that reached the fuel, so from the laser through the gold through the pellet, and then actually reaching the hydrogen isotopes, that energy that finally reached the isotopes was less than the energy that was emitted back out, which is the goal of fusion, which kind of breaks the second law of thermodynamics. You can't get more energy out than you put in. Now, with that said, to clarify why it's not there yet, is that overall there was this energy put into via the lasers to overcome was still greater than the energy that was got out. So the energy that had to be transmitted to eventually get some amount of that percentage of that energy into the fuel was still greater than the energy that we got out. So not quite fusion yet, but again, one step closer, and hopes that there is that this will become a reality for limitless clean energy, hopefully in our lifetime. It's a good article. It's a good read, and also talks about some of the additional challenges. Yeah. All right, so let's go ahead and let's wrap that up. All right, so I have received a few emails and comments, people wanting to know what is systems engineering. I guess people have seen my website or my resume, so and I got a master's in systems engineering a few years back from Johns Hopkins, and so I guess that gives me some credibility to discuss what I think systems engineering is, or was, or is, or should be. Anyway, so we talked about a few episodes back, there's all these engineering disciplines. There's electrical engineering, there's mechanical engineering, there's civil engineering, structural, aerospace, aeronautical. There's all these different fields of engineering. And they're all, the application of scientific principle and design standards to produce tangible and useful products. So we call those more of the design engineering disciplines, because they're very concerned about, again, applying math and scientific principle and design standards for whatever industry or whatever discipline you so choose to pursue. And so for me as an electrical engineer, there's principles like Ohm's law, Joule's law, Kirchhoff's law of current and voltage. So there's all these laws. There's the language, the voltage, current, amperage, the formulas behind it, and then designed principles like we talked about. I don't know if it was in this video series or another. We talked about things like, there are kind of design patterns, a voltage divider, a current divider that you use over and over in different circuits. So that's all kind of that I would call it in the weeds. It's very detailed. It's very specific to a discipline. So oppose that to systems engineering. So systems engineering is at a much higher level, and when I say that, what I mean is it's not so much a technical discipline as it is a project management, a business management discipline through the lens of engineering. It's still technical in that you are managing highly complex systems, or the system development, but it's not worrying about how to design a component or a system or a subsystem. You are worrying about the system as a whole, or the product as a whole. So for instance, let's say you are building something kind of complex. Let's pick something out here. We'll go with what I know. So let's say you are building an aircraft. think of all the different disciplines that would be involved. You'd have propulsion engineers, electrical engineers, control systems engineers, um, aerospace engineers. You have all these different disciplines and people that have been brought up and trained classically in all those disciplines. So, obviously, you'd have the best aeronautical engineer for developing the airframe, the best propulsion engineer to develop the engines, the best electrical or control electronics engineer or avionics engineer to build all the control elements and the um, even human machine interface folks um, to design how does the flight control. So all these different disciplines have to come together to develop a product. And there's a great picture, and I wish I brought it up early, about a swing and all the different interpretations of a customer. Basically, it says a customer wanted a rope swing, a tire on a rope tied to a branch, and it shows all the different people that were involved and how they translated what that requirement went. Basically, the customer said, "I want to be able to swing from a tree." Um, and depending on how you look at a project, you interpret requirements differently. Systems engineering tries to avoid that. Basically, there's a thing called the Systems Engineering V. And let's see if I can bring up a copy of it here. It's a way of thinking. It's a kind of a process of how we build. So let's see if this is a good picture. Let me see if I can. Good. Yeah, this is a good one. Not too bad. Let me go ahead and share this real quick. Okay, so this is called the Systems Engineering V. It's the process by which you develop complex systems. So on the left, you start up here and you do things like first you have to get requirements. So someone has to come to you with a list, a need. It can be a customer who's going to have very specific needs, or it could be, if you're more in the consumer space, you're going to be trying to respond to the market needs and what we think customers want. And those are two different worlds. That's probably actually something good to talk about in a future episode. The difference between designing a custom product for a customer who's got specific requirements, specific budget, vice building for the consumer space. That's a little bit more fluid, but I digress. Anyway, so you start with things like very, very top level requirements. We talk about concept of operations. What am I trying to accomplish? What do I need to do? You haven't thought of you don't know if this is going to be hardware, software, and you shouldn't. You should be very open-minded that we don't know what the solution is going to look like when you're this very along. Basically, a customer just needs to come to you with a set of either it's a problem that they're facing with their existing hardware, or their situation that they think they need a technological solution to overcome. So you identify those. You get it out on paper. What am I trying to accomplish? Then you take those and you develop requirements. And then once you've got functional requirements, you can then decompose those into functional requirements, and then you start getting into very top-level design. You kind of start allocating what's hardware, what's going to be software, how am I going to do this, what kind of systems will I need to build, what kind of subsystems will I need. Then you get into the detailed design, and this is where the hardcore, quote unquote hardcore engineering occurs. The electrical engineers go off and do their part of the requirements. The aerospace engineers goes off and does their part of it. The propulsion engineer goes off and does their part of it. So you've got all these people working in parallel. Then you do things, you develop it, you build it, and then you have to integrate it. So now you've taken all these disparate parts, you have to now put them back together to make an actual system. And then you come on the way back up, you integrate it and you test it as you go along. So, and in the middle you have those arrows that connect, concept of operations to system validation, system requirements to system verification and deployment. Because as you're designing, as you're starting at the very high level requirements down to the high level designs, you want to be thinking, how am I going to test this later to actually verify or validate? And there's a difference. We'll talk about the difference, what that means. If it's 6 months, a year, 18 months, or God forbid if you're into defense programs where it's many, many, many years later. How am I going to test that I've actually built something that works and is meeting the customer requirements? So as you're going along the design, you've got to be thinking about, how am I going to test this? And then you get to the point where once you've built the thing, you have to do unit testing. So the electrical engineer tests their little part, then you put it together into a bigger subsystem, and you test that subsystem. It's modular design. You test the subsystems, and then you put all the subsystems together, and you test the overall system, and you do verification, and then you do system validation, and then you actually, once you're done, the system is validated, then you go off, you operate it, maintain it, you make changes over as it goes through its life cycle. But so this is what systems engineering does. This is the kind of work a systems engineer does. They kind of cut off at the detailed design. At the detailed design and the unit testing, they rely on design engineers. So a systems engineer does all the work down to and then back up from this kind of mid-level part of that V. So verification, validation. The difference is, the way it was taught to me is, verification is, did I build the system right? Validation is, did I build the right system? So verification, did I build the system right, is basically answering, let me go back to my blueprints, my schematics, and did I actually build what I thought I designed, and does it perform within the constraints and the parameters that I established? Then validation is, now did I actually build what the customer wants? Did I build the right system? Is this actually going to meet what the customer needs? They're not going to care about, how the current flows and the voltages are dealt with in the components. They don't care. They want to know that I wanted an airplane that could fly at 50,000 feet for 10 hours on 5 gallons of fuel. That's what the customer requires. That's what they want to know. And that's that final validation. And that's the difference between verification and validation. I can go into more detail with this later if there's specific questions, but systems engineering to me is kind of like being the conductor of a symphony, except instead of having musicians, you have engineers of different disciplines. So where you've got the woodwinds, and part of it because I know nothing about music. So you've got the wind instruments, you've got the drums in the back, you've got the violins and the string instruments. Well, same thing with engineering. You've got electrical, you've got propulsion, you've got aerospace, you've got avionics engineers. You have all these different types of engineers. You, as the conductor or the systems engineer, have to make sure that no one discipline trumps the other. That you're building what's called an optimized system. You don't want to optimize a component or a subsystem at the expense of the overall system. You want a system overall that works optimally. So a systems engineer kind of helps. Where do I put my money? What kind of what should I be testing? What shouldn't I be testing? Because again, you're going to be constrained with also what's called the V, or not the V, the requirement, the triangle. So basically, if you imagine a triangle, On one side, you've got costs. The other side, you've got schedule. And then down here, you've got requirements. And I've also seen it where then you take all that, you put it in a circle, and that's the customer expectations. So I can give one two. I can make changes to two as kind of like the dependent variables, and the third is always going to be an independent variable. It's always going to react to the other two. So if you care about cost and performance, it's going to then what you can't control is schedule. If you care about cost and schedule, then you're going to have to give up requirements. If you care about requirements and schedule, then say you have a very tight schedule but you want a very high performing system, you're going to have to eat a lot of cost. It's going to be a very expensive system to develop. So a system engineer helps maintain that triangle based on either if it's a product you're developing within the business that you hope to sell to people, you've got to, you don't want to put your company into bankruptcy. And if you're building for a customer, if you're building a custom based on customer requirements, the customer's going to tell you either they're going to do a fixed fee contract or they're going to do a cost plus with some sort of ceiling that says, I'm only going to pay you up to this amount of money, and I'm going to demand that to be met on this schedule and meet these requirements. And as a system engineer, you've got to kind of help your project management team control that. Wow, systems engineering. It's more management. It's more intangible engineering, but I find it absolutely fascinating. I love it. Not everyone does. A lot of people like to be design engineers for a career. They care about the technology. So you have to make a decision on what your interests are. I personally, and this is again my bias, I would not study systems engineering as an undergraduate. I don't know a lot of schools that do offer systems engineering as an undergraduate. Certainly my alma mater did not. What I would recommend is picking a traditional engineering discipline to study as an undergraduate. So go get an electrical engineering degree, go get a computer engineering degree, go get a mechanical engineering degree. Learn the technical trade. Go off, work a couple years in that trade. And then, after you've got 5-7 years of experience under your belt, then go back, and if you're really interested in project management, then go back and pursue a systems engineering degree. That's my personal bias, because maybe that's because what I did. I just think you'll be better off, and you'll be better serving your customers in the future if you have a technical background at the detailed design level. With that said, there is an inherent risk to that also. Like anything in engineering it's a double-edged sword. It can go both ways. So the problem with having a very detailed design background is that when things get hard, when you don't know which way to go and you're the project lead, you kind of tend to resort back to that which you do know. So if you're an electrical engineer and things are hard, you try to turn everything into an electrical engineering problem and solve it that way. If you're a mechanical engineer by undergraduate degree, when you face an insurmountable problem or a seemingly insurmountable problem or a roadblock in a project, you'll want to design a mechanical system to fix the problem, and that's not always the right solution. Which is why good system engineers really are generalists. Even though they have a background in a specific discipline, they are not afraid of going out and learning about what a mechanical engineer does, what a civil engineer does, what a structural engineer does. because they're able to then connect the dots between the disciplines, and they're a little bit more comfortable when you're in a design review meeting to be able to know a little bit about every discipline. So that's how you have to kind of um, balance yourself. Don't always, if you find yourself always thinking that everything is you know if you're an electrical engineer and you think everything can be solved through electronics, or it's an electrical problem, pause and think maybe they're not. Maybe there is a better way to do it that's in using a technology or a practice that's not a part of my design background or my knowledge base. Go out and seek other professions of other disciplines and bring them in, and that makes a real good systems engineer. Someone who's not afraid to talk outside their traditional background. So, gosh, that's it. Um, Systems engineering in a sort of a large nutshell. I probably rambled on there for a bit. Um, so anyway, let me go ahead and wrap up this week's episode. Um, as always, you can follow along at steampowerpodcast.com throughout the week. There's links to our Google Plus community. There's the links to my Twitter account. We post articles throughout the week, anything that's interesting about science and technology, engineering, a little bit of art, a little bit of math. So that's all there. What else? Again, audibletrial.com/steampowerpodcast. That helps us a little bit pay the bills on the podcast. And, geez, I think that's it. Again, if you hit the website, if you've got ideas for an episode, if you've got stories to share, I encourage you to check out the Google Plus community. Yeah, I think that's it. I'll stop rambling now. So with that, thank you very, very much for listening, and until next week, thanks for listening, and stay quirky. Okay. All right. And if you're still sticking around, that's just to end that for the audio podcast. I'll go ahead and cut the rest of this out, but I just want to spend a little extra time to see if I can figure out how I can get rid of this little green here. Yeah, I think it worked out. I think it worked out okay. Let me know. Just take a look at here. Appreciate any comments, and if you got any advice, I've got it pretty well lit. I am in my basement, so there's not a lot of other, and it's in the evening, so not a lot of natural light, but three pretty big light boxes here. Gosh, what else? Nothing really. Oh, makerspaces. If you have a makerspace in your community, or if you don't know, get on the internet, Google search, take a look. Had a really great class this past week on Blender, which is a 3D modeling, animation, movie making tool. And I had tried to use it before in some other things like Google SketchUp, and I just never. I can't do. When it comes to technical things like that, YouTube videos are hard for me to watch because I like to interact. I like to be able to ask questions, even if I don't. I like to know the feeling that I can. And frankly, I think as I get older, I'm developing a little case of ADHD, so it's hard to sometimes focus on a video. I think group settings are the way to learn, and kudos to the guy that taught it at our makerspace. Really well done. I think there's a lot of goodness in learning from someone who's not an expert. kind of like the way, at least I think the Navy, trains pilots is, you go into the Navy, you get your commission, you go through flight training, you go out, you fly a deployment, and then you come back and you train the next generation. So you're not too far, 3, 4 years later, you come back and you're now a flight instructor. Um, and what I, not being a fly guy, what I was explained is that's um, because you're not that much older than the people that are coming through the training pipeline a few years later. You can relate more, and B, you haven't flown so much where it's so second nature that you leave out the little details. And that's a problem with a lot of the videos, especially when they're done by like guys that do it for a living. Um, it's not that they're bad. It's not that they're doing it on purpose. It's just sometimes there are keystrokes or there are menu settings that you just take for granted because you've been doing it for 5, 10, 20 years. Whereas learning from someone who's only been doing it for a couple weeks, a couple months, maybe a year, they're still in tune to what it felt like to be a newbie using a piece of software or a design or whatever. Um, so that's why, like I said, I really encourage maker spaces. Um, Go out and get for me it's really, as a professional engineer, I have to do continuing education, and a lot of that continuing education, unfortunately, is not the best. It's a lot of it is death by PowerPoint, and it's because there's a guy, he's done 25 years as an engineer, he doesn't want to work anymore, but he still wants to keep his peace, so he teaches classes. And unfortunately, the classes are so god awful boring, um, especially the ones that are just by PowerPoint. Compared to, and those count. Those, I can take those classes and send them into my state board, and every 2 years I renew my license, and I'm good to go. Classes that I took at my makerspace where I actually hands-on learned something that I did not know before that I can go back and apply to my career, unfortunately doesn't count for my continuing education, and I think that's a shame. Um, and that actually goes into another discussion we'll have in another episode, maybe in a week or two, about the future of education, especially technology and engineering education. you know, do you really need to go to college? Um, is there a better way? As the maker movement really takes off, and I don't think it really even has um, taken off to its full potential yet. Um, really has a chance to revolutionize education. The problem with education is that we treat it like it was 50 years ago, where there were advances in technology, but they were at a glacier pace. Today things move so fast that the educational construct that we have of 4 semesters, or 8 semesters over 4 years and 13 weeks at a time, doesn't make sense anymore. But I don't know the how you replace that fully. But I think it's something that we need to collectively, as a society and as a profession, think about. Anyway, I'm going to done ranting now. So thank you for everyone who stuck around after the official end. That's my rant, and with that, I'm going to go ahead and hang up now and then go enjoy my Saturday night. So again, thanks for listening, and again, I'll say it one more time. Uh, until we cross paths again, stay quirky.